Good afternoon. My name is Amit Goyal. I am at the State University of New York, SUNY, at Buffalo, New York. Welcome to this inaugural session of a new NAE webinar series highlighting current and consequential issues in engineering and public policy examined in the Academy's flagship publication, The Bridge. The first webinar will focus on the Materials Genome Initiative, MGI, that was featured in the fall 2025 issue of The Bridge. So I would like to thank the Bridge Editor-in-Chief, Ron Latanessian, first for having such excellent and timely topics covered in The Bridge, and for the fall 2025 issue to focus on the Materials Genome Initiative. And second, for initiating the NAE Bridge webinar series for broader dissemination of the issues discussed in The Bridge. Next slide, please. So the fall 2025 issue of The Bridge, for which I served as guest editor, had 7 articles containing perspectives from leading national and global leaders in MGI who are developing strategic plans and policy across federal agencies, as well as from research and innovation leaders working in key areas such as autonomous experimentation, self-driving laboratories, advanced microscopy, polymers, plastics, and energy storage. These articles provide state-of-the-art reviews, summarize progress to date, and offer recommendations for future work to fully realize the goals of MGI. You will first hear summary remarks from an author representing each one of these 7 articles. Following this, we will have a panel discussion with these 7 representatives, 1 from each article, who will serve as panelists. We will also take questions from the audience for the panelists. This webinar is being recorded and will be posted on the NAE Bridge page. Next slide, please. So the first article in this issue was titled Accelerating Materials Innovation, Lessons Learned and Opportunities Ahead. The authors were Lisa Friedersdorf, Principal Assistant Director for Physical Sciences and Engineering and Executive Director, National Science and Technology Council, White House Office of Science and Technology Policy, and James Warren, Director, Materials Genome Program at the National Institute of Standards and Technology, NIST. The remarks will be given by Jim. Go ahead, Jim.
All right, thanks very much, Amit, and it's really a great pleasure to be able to do this. I think it's also really nice that the National Academy is doing this and featuring out the MGI. So I'm going to talk about the initiative at the sort of highest level and agency support and our key objectives now and thrusts. And I think that you'll see with the ensuing talks sort of where the MGI has landed and its relevance. It's only increasing with time. So yes, thanks. Next slide. So this is a hasty look back. So I like to start with this. So in the mid-90s, colleagues and I stood up what was at that time the second website at NIST. This is when we were back explaining, what the World Wide Web was to our senior management, and they were asking us if we could print it out and things like that. And if you could hit the advance one more time, I believe a little thing will come on the bottom. Yes. And so the center's mission, and I had to use the Wayback Machine to capture and find these old websites, was in no small part, the third bullet says, to develop powerful new tools for materials theory and modeling and accelerate their integration in industrial research. And the idea back then was we really believed that we wanted to move just beyond archival publications and make the codes available, because we viewed the codes themselves as far more valuable in many cases than just the archival research. And that sort of idea has sort of been driving my career and a number of my peers' careers for much of the time. And so let's go to the next slide now. And if you look at sort of the history, in particular, of government funding around supporting theory and modeling and elevating its importance with respect to experiment to being as sort of on a par, there's actually quite a long history, not surprisingly, of this, and it came under various names and various government programs. Certainly, you can see a lot of these, and they will be quite familiar if you've been following the history of government funding in these spaces. One might feature out particularly the Accelerated Insertion of Materials program at DARPA around the year 2000. And then there were some very influential National Academy reports, actually, including the 2008 ICME, or Integrated Computational Materials Engineering, which then formed the core what became the Materials Genome Initiative announcement in 2011. So fast forward one more. So the way I tend to think of the MGI, of course, is in then the context of modeling. And so on the left, of course, you're just looking at a CAD picture, which really revolutionized, I think, the way that a lot of engineering was done. Uh, and then on the upper right, you're looking at finite element modeling, and that can now be done by your standard, not standard, but a sophisticated undergraduate can certainly, apply these tools now and use them to great effect. And then in the lower corner, you're seeing microstructural predictions that were done in collaboration with some colleagues in Hungary. But the point here really is that we are moving to finer and finer scales and able to predict more and more about materials themselves. And so the opportunity to massively accelerate uh, uh, materials by design was certainly in reach. And this was sort of the vision we'd arrived at with the announcement of the initiative. So we can take the next slide, please. So the initiative itself was, as I said, rolled out in 2011, and it was really not so much about, well, how do you do multi-scale modeling, but how do you hit the slide advance one more time, please? Create an infrastructure so that it is easier to do this in general, right? So the outer ring is all the things you can achieve with better materials, and there's nothing terribly surprising there. But the infrastructure to do this is typically difficult and expensive. And so the idea behind the ImageAI was to really roll out the tools, computational tools, and experimental tools, of course. It wasn't just about modeling, it was about raising modeling up to appear and then getting a nice tight integration of that with the digital data and create this infrastructure. So that was, the whole motivation behind the MGI. And then, of course, we needed a workforce to get this done. Next slide, please. So the MGI is an initiative, which just means that there's a statement by the White House that this is important and bigger than the mission of any single agency. And so many of the agencies have been active participants in realizing the vision of the MGI over the last 15 years now of its existence. The first 5 I've listed here have been very active. And it's now spanned into the 4 administrations. And there are certainly looks like changes afoot. But nonetheless, the ideas stand. If you go back and you sort of think about what the MGI is from my own point of view, right? We're all trying to do something like what we used to call multi-scale modeling, right? We're trying to move from quantum to mesoscale, the phase diagrams, moving all the way out to the macro scale. But it's sort of naive to say you're just going to solve Schrodinger's equation and then somehow get, design for the best alloy for, an automobile and then do that. You actually have to make all sorts of decisions about what you're going to feed into this loops. In particular, what kind of data, what kind of models you're going to include. So if you could advance one more time. So what we're really doing is creating and capturing knowledge about materials, embedding that and encoding that in some kind of system, and then calling on that system to achieve the materials by design and the materials with targeted properties that are desirable. Next slide, please. So as I said, these ideas aren't terribly new in some sense. As I said, the real idea here is how do we lower the barrier, right? If I can get a single engineer to be able to do this, right, well, then we've really accomplished something. But this is, of course, hard. But next slide, please. So here's a nice example, I think, of the way industry now is doing this. And this slide is actually from 2018. So we've moved now my goodness, we're getting on close to 8 years since I grabbed this slide. But what was exciting at the time was SpaceX in particular, and that rocket engine is now able to go from clean sheet to a new alloy for a rocket engine deployed in 18 months. This used to be 18 years. And so what you're seeing is that these multi-billion-dollar companies are able to do this. It's still largely the provenance of multi-billion-dollar revenue companies. And so, there is still a lot for the MGI to do, but now we are starting to really see these kinds of approaches coming into their own. And in particular, what we're going to talk about, I think, for much of the rest of this webinar is where we are headed and what the promising techniques are to get these kinds of capabilities in the hands of almost every single manufacturing shop in the world. So next slide, please. So before I do that, I want to take a quick detour and talk about my own agency's support for MGI, because it's going to lead us, I think, into the rest of the discussion, which was our focus on data. So next slide, please. NIST has long been involved in provisioning the highest quality data to industry and to the general public when needed. That's really what our mission is, in no small part. And so we're like, well, let's focus our expertise towards the MGI, just like other agencies are going to take their mission focus and bring it to the MGI. So we've had 3 pillars in this support, which was enabling and enhancing the exchange of data. So how do you move it around? How do you ensure that people can find the information? This turned out to look like it was going to be easy. It turned out to be very hard. And there's still a lot of thinking about that. We knew we would have to focus on how do you assess and improve the quality of that information. That's classic NIST. And then the thing that we were somewhat visionary on was we knew that if we had all of this information, that we could now do data-driven materials research. Now, at the time, right, we were calling it that, but within a few years, we were using the term AI instead as the term of art. Next slide, please. So there's obviously a lot going on at the other agencies, and this is by far, as I said, the least of them. So NSF has their entire program, DMREF, where they're designing materials to revolution and engineer our future. And they also have the materials innovation platforms. DOE has the energy materials networks and many other supporting programs. And if you now look at the recently announced Genesis activity, a huge number of elements that have a long pedigree and traceability back to the MGI and across the DoD, and we'll hear more about that soon. And the service branches, lots of manufacturing, autonomous materials, characterization, fabrication, etc. So just a tremendous amount of vibrant and active stuff going on. And so, the article that, yes, that's fine to move to the next thing, which is lessons learned. I've been kind of talking about what's been hard, right? There's been a lot of success in using density functional theory. If you had told me 15 years ago that density functional theory would be viewed as one of the most valuable materials design tools, I would have said that's amazing, right? Because it used to be considered sort of a boutique area, only for the chemists and physicists who sort of snuck into the materials department. Now it's absolutely used widely in industry. There's a lot of successes came out of the ICME community, as I mentioned. The SpaceX example, new alloys were designed here for the Mint. They still haven't been implemented, but if someday maybe the nickel will be a NIST-designed alloy. And by and large, the successes of ICME were in metallic systems where phase diagrams are easy. Easy, that's not the right word, where phase diagrams were available, which provided a rapid materials design capacity. Polymer systems still hard. And so I think that there's a lot of room there. And the modeling is just frankly too slow, right? So if you have to use a supercomputer, opening things up here and saying what's been a challenge for the MGI, we can make predictions, but we'd really like them to operate at the speed of manufacturing, which means we need more data because we want to create AI models. And then there's been a lot of discussion over the decades around data sharing, but this remains a challenge because of the incentive problem. Next slide, please. So that means that we need more data, and I'm approximately done here. So how do we get more materials data is the real question that lies at the bottom I think, of all of this. So next slide, please. So here is, in my opinion, where we're headed. And this is, we go in a bit more depth in the article in the bridge, right? The MGI has developed many new materials, but inserting them into manufacturing is hard because you have to bridge across many technology readiness levels. Self-driving labs or autonomous experimentation can not only rapidly deliver those targeted materials, but while you're designing that material with the lab, you're also generating reams of data. And that data is, in fact, in some sense, more valuable than the specific material that you've generated, because that can be used to train surrogate models of materials, processes, and properties that can substitute for the traditional physics-based or chemistry-based models, which are often slow. They're still going to be the benchmark, but you now have something that's pretty darn good and maybe 6 orders of magnitude faster or something like that. These surrogate models can be being used as materials digital twins, which can operate at the speed of manufacturing, inserting materials knowledge into the manufacturing paradigm. So we're finally going to be able to realize taking our basic research and essentially including it now on the factory floor. And this is going to massively change all of R&D, in my opinion, and realize engineering impact for this kind of work. Okay, so last slide, or am I done? I'm done. All right, thank you.
Thank you so much, Jim. So the second article in the 25 fall issue was titled Revolutionizing Material Science and Technology to Secure Our Future. The co-authors were Richard Weyer, Chief Scientist, Materials and Manufacturing, Air Force Research Laboratory, Germano Inacchione, Director, Division of Materials Research, National Science Foundation, and Anthony Tony Roulette, U.S. Steel Professor of Metallurgical Engineering and Material Science at Carnegie Mellon University. The remarks will be given by Rich Weyer. Rich.
Thanks a lot. Good afternoon, everybody. Definitely on behalf of my co-authors, Germano and Tony, it's a privilege to share with you the highlights from this article. What I'd like to do is maybe I'm going to definitely build off of Jim's comments and his great overview of MGI and its successes, and try to maybe look at that challenge from even a higher meta perspective, in the sense of how does materials impact technology, not only just generate new materials and mature them, but what happens if we think about where they're going to go, and what does that mean to what we need to do? So I'll talk a little bit about the imperative, a framework maybe to consider those challenges, and some possible proposals for community and federal action. So the first slide's up here. Civilization and its technologies are based and limited on by materials at its disposal. I think this is taken as a fundamental fact by many of the people online. From national security, our prominence is defined by materials mastery. Go back historically, the Roman dominance of iron production led to their military might. And in the 20th century, American stealth technology, similarly, based on novel, innovative materials, is a differentiator in our defense posture. Similarly, from economics side, for a national economic perspective, leap ahead innovations inevitably evolve from new general purpose technology advances, materials being one of them. Just consider microelectronics. It is all about how do you control the crystallography, the purity, the dopants, and patterning to generate the 18A nodes that we have today. That is fundamentally materials and processing and manufacturing processing. So today, materials and their access in response to this is a geopolitical tool. Supply chains are being weaponized, and access to critical elements impede both defense and economic development and production. Also, investment prioritization at the government levels are based on materials. China, for example, funds material science second only to medical science. And the bachelors that are coming out of their universities grow at roughly 14% per year, which is about 5 to 7 times what the US generates. So this is the world we're living in, and the competition that anybody is faced with in taking ideas and bringing them to market. Next slide. So as Jim noted, one of these critical challenges for materials is the impedance mismatch or gap between materials maturation and modern design production cycles, which are at the 1 to 3 year. And suffice it to say, the few examples Jim mentioned, most materials are still on the 15 to 20 year cycle. Innovators and engineers don't want to add a risk associated with an immature material, one that's at a low maturation level. And thus their creativity begins with known and proven materials and manufacturing that are certified, validated, and trusted. This is why the F-35 today, our premier fighter, is based on 1980s materials technology. The MGI, its leadership and coordination across federal agencies that Jim mentioned, has made substantial strides, especially to accelerate exploration. And Jim touched on many of the examples I have in the left-hand side there, whether it is the 10 years of DEMREF with over 4,000 papers from new multidisciplinary teams, that production is now clocking at 1 citation per hour, that corpus of innovation that came out of DEMREF. Materials innovation platforms from NSF has led to access of facilities, centralized facilities for innovators, both small business and academic, whether it's 2D materials, solution chemistry, many more. Jim touched on NIST's materials data factory, facility. I forget, Jim, what the F stands for. As Jim mentioned, it's core to now the new Genesis initiative that was just announced from the Department of Energy. The last few years, the MGI has shifted towards trying to solve the problem of getting to that reduction in ideation to the marketplace. Things like the 2024 MGI challenges that are available on the MGI website is a way to synergize not just federal investment, but private investment, companies and academics to rally around challenges that we can demonstrate MGI principles, not just in addition to things like what Tesla and SpaceX has done. However, as Jim said, more definitely needs to be done. And the framework on the right-hand side is what we put forth in the paper to kind of help the community wrap their heads around what are the key hurdles, those impedance, where the impedance is happening, and hence where we need to accelerate for materials maturation. From ideation and exploration to a digital artifact that can be used in modern model-based digital engineering tools, there is a lot of steps that need to happen, many valleys along the way to install that trust so that they would use the tools, whether it is a material solution or a materials platform that can generate a variety of solutions. Things like capacity, reproducibility, predictive models, quantifying uncertainty, understanding survivability and environments are key before anybody will invest money in scaling. And then before it is certified for a specific product, things like availability, reliability, manufacturability, sustainability, affordability, and integratability, and the necessary design and data tools need to be established before it actually can be used in product or even demos for new ID technologies. And the thesis that we talked about in the paper is that MGI and the acceleration has to be across all these if we truly want to reduce materials to product so they're commensurate with modern design production cycles. Next slide. So as Jim mentioned, key to that is harvesting the digital revolution. I kind of think of that as the intersections of artificial intelligence, machine learning, big data, high performance computing, and automation. But at the core of all that is data, uh, quality data and the data that's needed and accessible data, what's called fair data principles. And the challenge I feel that the community is facing, the materials and manufacturing community, is moving towards a data-centric discipline so that we can generate digital artifacts that are plugged into modern-based digital engineering. Some of the challenges that we really need to face along these lines that we talked about, the prerequisites to the maximum impact is, ways we can concepts to provide safely sharing data. A lot of ideas and projects going on in the community, such as using blockchains, like used in health and finance, to secure data and ensure pedigree of it, standards so that we can get workflows and the data can be transferred between tool sets, and even coming up with common workflows so that the data that comes out is lower uncertainties. There's great successes in the bio community, for example, along those lines. So it is really harvesting the innovations from other communities on how to create and access high quality data. But also one of the key things is to think about moving towards data as having value, and having, instead of data repository, data banks, where the data can be put in and it grows in value. Because at the end of the day, industry and many others will share data when they can find a return on investment on that data. So concepts out there that encourage that, or policies that do, I think would have a great impact in moving us forward. So such foundations that I'm talking about is paramount to autonomy and other digital technologies to really accelerate that pipeline, that synergy of autonomy and automation and AI, and to generate data and to do it where the researcher is on the loop is an exciting innovation. But we need to make sure it's applied where the impedances are at and the largest bottlenecks are if we're really going to accelerate the process. So what can the federal government do? What can the community do to try to bring these ideas to fruition? The article spends some time exploring those areas, and I'll just highlight three of those. The federal government has a very important role in brokerage, in policy and infrastructure and prioritization, so that we can augment the market forces. As Jim said, there's some examples in industry of great successes, but the question that we really need to face is, why haven't it exponentially exploded across all industries? And some of those reasons are just some of the investment timelines of industry is a lack of patience for long-term high-risk maturation. So there's definitely a role still for the federal government to continue to invest, not just in exploration, but all the necessary policy tools along the way to make sure that pipeline is trustworthy. The other is, how do we bring the ecosystems together? And there's been many great examples over the last decade of academic, government, industrial partnerships, these public-private partnerships, bringing together the community that's not only the innovators, but the users and the manufacturers to talk about what are the key hurdles instead of passing technologies over a fence or through a hole, looking forward and looking backward together to help prioritize. These have been incredibly successful in areas such as additive manufacturing and electronics, and I believe also has huge potential in cracking the nut on data valuation for materials acceleration. And then finally, unless we have a workforce that can envelop and articulate and push forward these ideas, not just in the science side, but across the board, whether it's in industry, finance, policy, all of these need to have a workforce that is materials, data, materials digitization literate. And so there's huge roles there for the federal government to also lead and continue to stimulate that education, not just in the undergrad and grad level, but across the board. So thank you guys very much, and looking forward to the discussion.
Thank you, Rich. Next slide, please. So the third article in this issue was titled Accelerating the Materials Genome Initiative with Self-Driving Labs by Milad Abolohassani, Alcoa Professor, Department of Chemical and Biomolecular Engineering at North Carolina State University. Milad?
Well, thank you, Amit, for the kind introduction. Hello, everyone. Good afternoon. I want to thank the NAE for organizing this very timely special issue and giving us an opportunity to have this webinar. So for the next few minutes, I'm going to talk about how self-driving labs or autonomous robotic experimentation can help accelerating the goals of Materials Genome Initiative. And I'm glad we had those two talks. I don't need to spend a lot of time on MGIs. Next slide, please. So we're always looking for new materials. It doesn't matter the scale of the problem we are trying to solve in academia or industry. We're always looking for new molecules or materials. But the problem is that when you're looking for a new material, you're always dealing with this, what I call a material universe. We don't have a map of this universe, and we are mostly blindly searching through this space. So the goal of MGI that was initiated in 2011, next slide, please, was to reduce the cost of material discovery by half and accelerate the speed of finding a new material by a factor of 2. So that was the initial goal, and it invested a lot of resources in computational infrastructure and data infrastructure. And the goal was to focus a lot on visual screening and having very powerful visual screening tools, and then validate the visual screening predictions by experiments, as Jim gave us a really nice overview and history of MGIs. Next slide, please. So MGI has been very successful. If you click next, in creating that computational infrastructure. If you click next again, it's going to bring some lists of success of MGI over the last 14, 15 years. Now we have very powerful high-throughput DFT screening tools. And I've listed the successes that I think are the key. I'm not going to go through all of them, but the most important one was actually the last one, establishing a foundation of data-centric culture in material science. So MGI was the nucleus of focusing on data in material discovery, but it focused a lot on computational part. And in the last decade or so, we've all learned that computation is great, but we also need a lot of experimental data. Computation alone cannot solve our material discoveries in the time scale that we need. If you click next, that's going to have a list of, if you click next, can you click next? Yes, great. So here are the list of challenges that MGI, I believe, has faced over the last 15 years. And it all centers around experimentation. There was no major focus on experimental workflows, increasing the throughput or capturing data metadata, or standardized way of capturing data metadata of experiments. And coupling computation with experiment was not properly, I guess, defined in MGI. And the last report of MGI 2024, this need has been highlighted that we need autonomous experimentation. So if you click next, now along the lines of MGI in the last 15 years, there has been new advancements in the way we do experiments. So this is the way we conventionally do experiments. We send our highly trained scientists in the lab. They spend 70–80% of their time just doing repetitive tasks. At the end of the day, they look at their data. They've done 1 to 5 experiments during the day, and they mainly rely on their intuition to decide what's the next experiment to do. So this is what I call a human-centered closed-loop science. We've been doing this for hundreds of years. But this is one of the reasons that we could not accelerate material discovery by 10 to 100 times just by computation alone, because our experimental throughput and the way we were doing experiment in the last 15 years when during the MGI time was not coping with the needs of the computations. In the last 10 years, high-throughput experimentation, robotics, and lab automation have advanced significantly. If you click next. So by bringing robotics, lab automation, if you go back, please, one slide, 31. One more, if you go back. Yes. So if you bring robotics lab automation in the lab, and you build these end-to-end automated experimental platforms and use all the recent advancements in AI machine learning to analyze the data, the high quality, high quantity of experimental data generated in the lab, we can go from human-centered closed-loop science to data-centered closed-loop science. This is what we call a self-driving lab that can accelerate the design, test, make analysis, DMTA cycle by 10 to 100 times. So this advancement started happening over the last decade. And in this article, I'm articulating and arguing how this self-driving lab can actually help MGI's vision to come to fruition and accelerate materials discovery, not just by a factor of 2, but actually going to 10 to 100 times acceleration. If you go next slide, please. We click next. Great. So what self-driving lab basically wants to do is to go from the siloed nature of the way we currently do experiments, that we have a separate wet chemistry lab that we're doing chemistry or material synthesis. We have a separate analysis analytical lab that we do characterization, and we have a separate facility just for data analysis and decision making. The goal is to go from the siloed nature of doing experiments to a unified lab. If you click next, there should be a new graphic that shows this is how a self-driving lab operates, that you have everything. It's like an all-in-one lab, that you have the automated high-throughput experimentation, the characterization, data analysis, and decision-making happening all within the same footprint. And we can close this time gap between running an experiment and making a decision about what should be the next experiment to do. And this is not going to replace the human scientist. This is why we have 2 human scientists in that graphic demonstration. So this is like co-pilot, a robotic co-pilot to human scientists. If you click next, and it can basically help human scientists to work on multiple problems, not just one problem over 5-10 years. With having access to the self-driving labs, we can work on tens, hundreds of problems within a decade. And we can reduce the material discovery, manufacturing time frame. We've already done 10 to 100 times over the last decade. There are examples that cited in this article that have already accelerated material discovery by 10 to 100 times, but definitely there is room to go even to 1,000 time acceleration. If you click next, so here's how a self-driving lab works, which is complementary to the infrastructure, the computational infrastructure already been developed by MGI investments and research over the last 15 years. So if you want to think about MGI, it starts on that informatics part, virtual screening of materials, and that leverages a lot of the infrastructure already developed by MGI. You define a problem, for example, a specific semiconductor material you're looking for with specific band gaps. You can use a virtual screening tool to down select some potential materials, but there is still in the virtual world, and we don't know if they're synthesizable. We don't know if those are the best material for the target properties and application you're looking for. This is where the self-driving lab comes into play. It bridges that virtual world and the physical world, and takes those hypotheses and prediction by the computational resources and goes through this loop of autonomous robotic experimentation to test the synthesizability and the hypothesis created by that virtual infrastructure. A lot of benefits that you get out of this self-driving lab or autonomous robotic experimentation. I'm not going to go through all of them, but the most important one is that reduced time to solution by 100 to 1,000 times here. If you click next, now this is how this self-driving lab vision and paradigm can activate the MGI knowledge loop. If you click next, using active learning instead of just brute force testing of materials predicted by very powerful virtual screening workflows, and then connecting the simulation with experiment feedback, and then transferring across a different material system instead of having very niche models for a specific class of materials. We can actually start looking at transfer learning across different domains of science, in physical and even life sciences. If you click next. So here's an example of one of the self-driving labs developed over the last 10 years. If you click next, this one was called AlphaFlow, but basically the goal was, can we find a new way of synthesizing advanced functional materials? These are heat-treated nanostructures used in photodetectors, LEDs, and even solar cells. If you click next, it has some of the performance. So here it's using a new way of doing experiments and synthesizing materials, miniaturized way of synthesizing materials coupled with reinforcement learning that basically models the actions and the rewards of taking actions in next steps of experiments. Same thing that was used in Google's DeepMind, the same type of machine learning pipeline. And in this example, within 1 month of doing autonomous experimentation, this self-driving lab was able to discover a new way of synthesizing these highly valuable functional materials, inorganic semiconductor materials, with better properties, faster synthesis time, and in a scalable manner. Within 30 days of autonomous experimentation, that outperformed 15 years of academic literature working on these materials by just using human-centered closed-loop science. So here's an example of how human AI robotics experiment collaboration under this self-driving lab paradigm can accelerate material discovery to help MGI accomplish its goals. If you go next, please, next slide. Here's the way how it operates. Miniaturizing experiments, so we need new modalities of running experiments, and to increase the data throughput. In this case, this platform was able to collect more than 600 experiment data per day. Using gold standard methods, you can maybe do 5 to 10 experiments a day. Here, you could do more than 600 experiments a day. If you go next, basically, these self-driving labs can help us create the right data or AI-centric data that can complement this computational infrastructure that has been developed over the last 15 years. Now, how can we go to the next level, and how can we help with accomplishing the vision of accelerating materials discovery? There's only so much you can do with one of these autonomous labs. We need to start thinking about how can we have this federated learning across different autonomous robotic experimentation facilities and infrastructure. We need to start thinking about how can we actually transfer knowledge across different labs, and how can we have recipes of materials shared between different robots, different modalities of doing experiments. So this is where we have to start thinking about how we can have distributed version of these autonomous labs around the country. If you go next, in order to move towards this federated learning, to actually materials discovery with self-driving labs, we definitely need to focus a lot and invest a lot in the infrastructure, and we need to make sure that we can have standards for developing high-throughput experimentation robotic platforms within this autonomous robotic experimentation infrastructure. If you go next, click next one more time. So in a federated mode, you can imagine like having a fleet of self-driving cars that's going to be much more efficient in transportation than having just manual cars. When you have a fleet of these autonomous facilities connected, sharing data, we can have this federated learning that can significantly help us accelerate material discovery. But a key challenge there is solving this scalability of these autonomous labs and sharing knowledge across a different variety of different platforms that are doing the same type of chemistry material science. If you go next, that's the last slide I think I have. So I think some of the areas I've highlighted in the article in terms of how we can move from these early demonstrations of SDLs or self-driving labs to national facilities, that we can have this distributed infrastructure across the country to both train the next generation of workforce that is ready to use AI and automate experimentation, but also in order to really be competitive in materials that are going to fuel the future of our economy, we need to invest in national infrastructure of these autonomous labs. And that's something that has started in some federal agencies, but I hope to see more in this year and next year. And that's all I have for my presentation. Looking forward to discussions at the end of talks today. Thank you.
Thank you, Milan. Next slide, please. So the fourth article was titled in the fall issue, Autonomous Experimentation and Self-Driving Labs for Material Synthesis Using Deposition Techniques. The co-authors of this article were Benji Maruyama, Autonomous Materials Lead, Materials and Manufacturing Directorate, Air Force Research Laboratory, Ichiro Takeuchi, Professor and Chair, Material Science and Engineering, University of Maryland, and Jason Hattrick-Simpers, Professor, Department of Material Science and Engineering, University of Toronto. And the remarks will be given by Benji. Benji, question. I got your latest version, but we still have the older one uploaded here on this file. Would you be able to manage with the version we have?
Sure. Yeah, that's great.
Okay, perfect.
Yeah.
Please go ahead.
Yeah, thanks everyone. Just wanted to say thank you on behalf of my co-authors, Ichiro Takeuchi and Jason Hattrick-Simpers. It's a great opportunity from the academies, and thanks again to Amit for organizing. And so just to give context from Air Force and Space Force and DoD side, right, we just have to go faster, right? That was Accelerate, Change, or Lose was already back now in 2020 as a dictum from our Air Force leadership. And so we need to go faster. Please, next slide. But really our context, right, is we never have enough money. We've talked about workforce a number of times, and we're out of time, right? We need to be able to go faster, whether it's responding to economic needs or, for example, new virus threats, these things, we have to be able to respond faster. And our research cadence of decades to bring a new material to market really is no longer acceptable. Next slide, please. So what is autonomous experimentation, also known as self-driving labs? Next slide, please. And so when we think about the way we're taught to do research, it's sort of like the game Battleship, if you played that. And what do you do in regular Battleship when you're playing? You poke around till you find a ship, and then you finish off the ship. But what we're taught to do is a reductionist decision policy, if you will, of keeping everything constant, changing one variable at a time. And you can see from the simulation that the traditional search method is not fast enough. And so what we need is experimental design as sequential decision making, where each new experiment is informed by the results of previous experiments. Next slide, please. And so we put our ARES, which is what we call our autonomous experimentation system, we built it into this 3D printer where the printer would print a little square. It would take a picture of it and then analyze how well it did. And based on how well it did and our objective, which is to fill in the square well, we would adjust the printing parameters. And what you can see is it prints, takes a picture, it changes, it does a new iteration. And over tens of iterations, the additive manufacturing ARES taught itself how to print this simple structure. So just a baseline example of closed loop autonomous experimentation. Next slide, please. And so for our work here, we thought about deposition techniques in autonomous experimentation, self-driving labs. Next slide, please. And for carbon nanotube synthesis, which is the focus of my deposition technique, of course, this is important for Department of Defense applications and in a whole range, whether it's lithium-ion batteries, sensors. You can go ahead to the next slide, transparent conductors. But we don't have many of these applications. Lithium-ion batteries are mature, but a lot of the structural applications are not mature because we don't have the science to make them at scale, as Rich was talking about earlier. Next slide, please. And so now a decade ago, we built the first autonomous experimentation system for materials, Aries, which taught itself how to grow these carbon nanotubes at controlled rates. So it did an experiment, it saw what happened using Raman spectroscopy. That's our vision system for equivalent of a self-driving car, and then used a decision policy to say, okay, here's where we want to go. We want to predict our growth rate. Here are the new settings that we can put our system in to make that experiment, see what happened, and again, iterate. And over hundreds of iterations, Aries taught itself how to grow carbon nanotubes at controlled rate. Next slide, please. So fast forward now to more recent work, we are now using Aries to more directly test scientific hypotheses. And so for this paper, which came out a couple years ago now, we tested the hypothesis, the activity of the metal catalyst for carbon nanotube synthesis would be at the maximum activity when the oxide of the metal was in equilibrium with its metal. And so that gets to thermodynamic equilibrium. And essentially we showed that that was true, and then we expanded that now to other metals. So we feel this is now a powerful tool to improve our science, which lets us now go forward and exploit that for scaling carbon nanotube synthesis. Next slide, please. So for Ichiro Takeuchi, who works also with Miklikma and Gilad at NIST, they are doing autonomous atomic layer synthesis. So how can we then deposit a layer, see what happened using read, and then try to use that read result to now optimize the deposition and the performance of their ALD deposited material. So their speed up is really 15 minutes per cycle, and that's a complete cycle of depositing the material, seeing what happened, and then deciding what to do next in a new cycle. Next slide, please. And they've now also expanded that to additive manufacturing for metals, and they showed that after 8 of these iterative deposition cycles, they were able to identify a very good condition. And you can see on the left-hand, the right-hand plot there, how the experiments are clustered around. So that means it's actually not trying to see all of the space. It's focusing the experiments on where it thinks it might find the best result. And so that brings huge efficiencies of the rate of progress. Next slide, please. So switching over to, next slide, please. To Jay Hadrick Simpers, who's at the University of Toronto. So he's doing electrochemical testing and using some very nice open source hardware that he's modified to do his electrochemical work, where he's essentially adding the catalyst, doing the electrochemistry, doing and measuring the results of the electrochemical results, and based on that, changing then the catalyst and the electrochemical scan parameters so that he can get best understanding of his electrochemical testing. Next slide, please. And now applying that to oxygen evolution and reduction electrodes, he's now able to essentially explore the parameter space, not just to find the optimal or the best OER, but to think about what's stable. So that stability gives you robustness in scaled processes. And so these high throughput experiments and transfer learning really define what the key descriptors are for predicting stability of these catalysts. Next slide, please. So now I'll shift gears from the demonstration of experimental work to the autonomous materials innovation infrastructure, which was really driven by MGI goals. Next slide, please. And just to say that there has been a step change in autonomy or autonomous in material science journals. So you can see starting in 2018, there's really a change in the rate. And we're looking at global investments. And so if we think about, Canada is putting in $500 million in this area, Germany about $1 billion, Singapore $250 million, China, we think the estimate is about $1 billion. US, this slide is a little dated now. At that point, it was about 200 million. So US is stepping up its investment, but the message is still there where the US needs to actually increase its investment in the area by quite a bit. Next slide, please. And to that end, we ran a workshop in support of the MGI strategic goals and had a group of federal government employees and other invited folks to essentially inventory what we had going, identify challenges and gaps. Next slide, please. And so I won't go through the results, but please check out the report. Rich mentioned this already, but we have a series of challenges that are meant to demonstrate what MGI and the AMII can do in things like tissue magnetic materials, composites, quantum, low carbon materials, and semiconductors. And so this is really a call to action. And so I encourage you to visit the MGI challenge page and also think about what we can do for the existing challenges and what new challenges we can introduce. Next slide, please. AI Aspirations was another event that really highlighted what AI can do for society, in this case for semiconductor materials innovations for sustainable microelectronics. Next slide, please. And the Programmable Cloud Lab, which is from NSF, Technology Innovation Partnerships Directorate, that's it's under evaluation now, and so I think that I expect that to do great things as well. Next slide, please. And then more recently from the White House in July, we have the AI Action Plan, which calls out AI systems and for novel materials, and so that's top level interest and direction in this area that says that not only is AI writ large, but that materials can be a core part of artificial intelligence. Next slide, please. And then finally, a memo from September for the FY 2027 R&D budget priorities really calls out advanced manufacturing, autonomous experimentation, and world-class research. And so that's between the White House Office of Science and Technology Policy and Office of Management budget. And then the last slide is where we need to go and emphasize what Milad already said. Public-private partnerships for autonomous experimentation are going to be required to move this forward. We need what's identified in the infrastructure and a primary vehicle to get that done. So the infrastructure, the workforce, all of those things need to be done together jointly through these kinds of consortia. And so that's my last slide. Thank you for your attention.
Thank you, Benji. Can we have the next slide,
Oh,
please?
sorry, that's one more slide, but we'll go ahead.
Okay, the next slide, please. So the fifth article in this issue was titled Self-Driving Microscopy for AI/ML-Enabled Physics Discovery and Materials Optimization. The co-authors were Sergey Kalinin, Chief Scientist, AI/ML for Physical Sciences, Pacific Northwest National Laboratory, and Weston Fullerton Professor, Department of Material Science and Engineering at the University of Tennessee, Knoxville. Stephen Spurgeon, Senior Scientist, Senior Materials Data Scientist, National Renewable Energy Lab, now the National Laboratory for the Rockies. And Vinayak Dravid, Abraham Harris Professor of Material Science and Engineering and Founding Director, Nuance Center at Northwestern. And the remarks will be given by Sergey. Sergey?
Thank you very much for the introduction, Amit, and it's a great pleasure to share some of the lessons learned over the 20 years that we applied machine learning for the electron and scanning probe microscopy. But to follow the topic, let's start with how the microscopy can change the material discovery paradigm. So there is a very famous statement by Santayana about 110 years ago that those who cannot remember past are condemned to repeat it. So now is not the first wave of interest for the accelerated material discovery. The first one happened in 60s and 70s when people were working on the diffusion junctions. The second wave that some of us remember was between 95 and 2000. That was the time when Ichiro Takeuchi started to work on the combinatorial libraries. So when I got to Oak Ridge, there was still a combinatorial research program that was defunded by about 2002. And there are several lessons learned from this past investment in the accelerated discovery. So the first lesson is that if we really want to achieve the result, we actually need to close the loop from synthesis to the characterization and model update. So if we just scale theory and if we just scale the throughput of the synthesis, that is actually not enough. So we actually need to accelerate the whole discovery loop. We know that ML and AI and predictive theory allow better initial choices, but at the same time, the reality on the ground is that most materials are discovered serendipitously even now, and I'll show the example of the material system where it is the case. And the third important lesson is that very often the characterization tools that we absolutely need to close the discovery cycle are limited by the fundamental physics. So when I started as the undergraduate student 35 years ago, it took about half an hour to do the laboratory X-ray. So now if I go to the facility at University of Tennessee, it still takes half an hour about to study the X-ray scattering. So generally, if we want to accelerate the material discovery, we actually want to use the 21st century theory and AI stack on top of the tools with the higher throughput, both for synthesis, and Milad have illustrated how it can be done, and also for characterization. So if you go to the next slide, what can it be? And the vision beyond the program that we are building at the University of Tennessee is that we actually have to go small to go big. That basically means that we want to use the characterization using scanning probes and electron microscopy to explore material functionality on much smaller volumes, so on the level of femtograms, and also on the much smaller time scale. So to characterize the structure using electron microscopy, we need less than a second. To characterize the ferroelectric or photovoltaic properties by scanning probe microscopy, we need times of order of seconds and tens of seconds, whereas the corresponding macroscopic functionality measurements would actually take us hours. And most importantly, this technique allows us to understand the chemical space of the defects that exist in the real materials. And if we understand those, what we learn becomes translatable to much longer term prediction of how materials will behave under the non-distribution conditions. It allows us to considerably shorten the early stage TRL transitions to the manufacturing, and so on and so forth. So if you go to the next slide, next slide, please. So the key question becomes, can we run the microscopes faster? So for the time being, microscopy is limited by how fast the human operator can introduce the command and how fast the human operator can explore some object space, and absolutely not by the intrinsic time scales of the instrument measurements. So we started this quest while I was still in Oak Ridge about 20 years ago. For the first 10 years, we went the pathway of scaling the throughput. So we were introducing the high-dimensional measurement schemes that allowed us to collect large volumes of data. So about 10 years ago, we got to the point that experiment can give 10 to 100 gigabytes of data per essentially single-day experimental campaign, set up the clusters to analyze it. And then we came up to one very important thing, that we cannot scale data acquisition. Rather than acquiring more data, we need to learn how to make better decisions, because better decision is much more reliable pathway than getting more data. What's interesting is that the same type of principle applies for the broadest range of the material discovery problem. So it's always about better decision and closing the loop faster rather than just scaling. But then if we want to run the microscope faster, we sort of find ourselves in a space where the number of possible operations is very limited. So if you want to measure structure-property relationship, you essentially look at the screen and choose where to take the detailed measurement. But then we started to realize that the driving logic of the human decision-making during the experiment changes quite a lot. So in the beginning of the experimental campaign, the human operator will work on the optimization of the microscopy. So then you will start to go to the a priori known regions of interest. Then you look for anomalies of some sort. And only after that, you go to the physical theory falsification. So in other words, the operations that we can run are almost the same, but the experimental objectives and the reward functions during the experiment are very different. So there were two lessons that we learned after that. So one is that we need to understand the principles by which human makes decisions. And secondly, there is a well-known principle that we want to save all the data during the experiment. So in principle, that's not exactly true, because the data acquired during microscope optimization is absolutely useless for the goal of the material discovery. So only mature data is useful. So if you go to the next slide, please, then we realized that if we want to build a smarter microscope and then scale to the smarter material discovery platforms, we need to learn to represent the operation of the instrument as the workflow, so the sequence of operation. And if we want to represent it as the workflow, we need to have both the hyperlanguage that allows us to parameterize what commands can machine learning agent give to the microscope, and also define the principles by which these workflows can be constructed dynamically. And it turns out that if we want to do it, we essentially have two options. We either need to have a fixed policy. Fixed policy means that we already know what we want to do before the experiment, and that's possible if and only if the field is sufficiently mature, like crystallography or semiconductor characterization. If we want to discover something new, there is a fixed policy doesn't work. It is the same type of problem that we have if we try to use supervised machine learning for the discovery problem. So supervised machine learning works if and only if we already have a lot of data. But if we have a lot of data, that means that the field is already not unknown. That means that we know quite a lot. If we have the reward allow us to formulate the principle by which we go into the unknown. That's a big difference compared to the supervised ML problem. Reward can be available at the single step, then we call it myopic. That's what Bayesian optimization uses. Reward can be sparse. That's what reinforcement learning tries to do. So next slide, please. So, and then the interesting thing that we realized is the question whether machine learning and physics is enough at this point to build autonomous systems. And the argument that I want to make that it's not necessarily the case, because obviously physics and data form a continuous spectrum. We have plenty of algorithms that have physics, have ML. Next slide, please. But this is not enough. So what we also need, we need to define the reward structures. Rewards can be very complicated, like beta energy generation, beta materials, whatever. Next slide. So rewards in physics and in data domains correspondingly are very, very simple. For example, in data, simplest reward is the loss function. In physics, reward is predictive power of the model or parsimony of symbolic expression if you subscribe to the Landau School of Physics. Next slide. But in real science, the rewards are somewhere on the spectrum between very simple that we're already using and very complex, which reflect the long-term societal requests. Next slide. So the question becomes, am I the only person who says that? And it, kind of as an example of very strong confirmation bias, this is a quote from the book by Peter Norvig that basically says that almost all AI research until now has assumed that the reward or utility function is known. And the point that I want to make that in material science or any real-world application, the reward function is almost never known. In fact, it's a hypothesis that we make that if this is a KPI that we want to accomplish now, that's what will allow us to accomplish the long-term goal. Next slide, please. And then we asked ourselves a question that maybe, just maybe, we already have everything that we need in order to build the automated tools. We have the algorithms. We kind of sort of have to build our own APIs that allow us to build interfaces between machine learning agents and the tools. So that's what my group practically does 50% of the time. But the area which is almost non-explored is the question of how do we specify the reward functions. So if we start from imaging, the obvious reward function is imaging optimization. So that one is relatively straightforward. Interestingly, a very simple reward function is physical law discovery. So about 5 years ago, we have demonstrated that we can use a machine learning agent, which has a list of possible hypotheses. So at that time, the hypothesis came from me. So that was before the LLMs. Now we can have LLM agent to do that. And then the microscope will automatically find out which of these hypotheses is correct. Now, what's the limitation of this approach? The approach is that for a single microscope and a single sample, the number of the hypotheses that can be falsified is very, very limited. So the third lesson learned here is that for no matter what hypothesis is generated by LLM or reasoning system, each hypothesis requires the experimental footprint. And this experimental footprint is associated with costs and waiting times. And the more limited is our experimental footprint, the smaller is the number of hypotheses we can realize. Next slide, please. That being said, next slide, please. That being said, automations start to work like a charm. So if you go to the next slide, even the simplest form of the automation allow us to explore complex material spaces. So what you see here is the example when we run the experiment that allows us to optimally learn structure-property relationship in the complex microstructure. So what you see on the top right is the automated microscope that explored the image space of the complex sample, and you see that it discovered what microstructural object has the optimal functionality. In this case, area under the hysteresis loop. And the great thing about this type of problem is that it is absolutely equivalent to the discovery of the optimal functionality in the complex microstructure space or molecules and so on and so forth. Next slide, please. That being said, our primary limitation is that we can have fast feedback times on relatively limited experimental platforms, or if we try to expand our material space, for example, combined synthesis and characterization, then things become slow. And for example, if I try to build a materials discovery workflow that relies on synchrotron, and I can access the synchrotron every half a year, I'm not going to get very far. Therefore, the challenge that for us become how can we expand our experimental footprint while we are staying within the constraint of the single instrument. And it turns out that what we can do is to kind of remember the past. And in this case, we can pick the combinatorial library. So all of us know what it is. It's basically the cross-section across the phase diagram, can be binary, can be quasi-ternary. Next slide, please. And can you please click on the video on the left? And this is the example how it works. So what you see here is the ternary combinatorial library that we put on the fully automated microscope. This is a very multi-step workflow. So it looks like it just acquires images and spectra. In fact, it's a little bit more complicated than that. So in this case, we have the automated optimization step of the imaging, we have the optimization of the spectroscopy, and we have the structured Gaussian process model that navigates the exploration of the combinatorial library space. Can you please click on the right video? So, and it actually practically works. So if you look at the second row here, you will see three maps. One map is the surface roughness. Surface roughness essentially tells us whether the material is thermodynamically stable or we approach the phase separation region. The map, which is right in the center, is the piezoelectric signal. So you can see that the ferroelectric phases emerge close to the phase stability. So interestingly, the ferroelectricity in nitrides was discovered in 2022, only 3 years ago, and it was not predicted theoretically. It was discovered serendipitously. And then the map that you see, which is on the right, this is the map of the hysteresis loop area, which basically tells us what is the pinning mechanism, and it immediately tells us where to pick the right composition for either ferroelectric storage or for the memristors. What's our gain here? So in this case, the total experimental time making the library and characterization is about a day, slightly less, but kind of let's be generous. If we were doing it sample by sample, that would be at least a month. So we have a very real times 30 acceleration for fairly high TRL discovery. So we are not discovering the property of material in the idealized setting. We effectively find the properties that are relevant to the device level deployment. So if you go to the next slide, please.
Okay, could we summarize soon?
Absolutely. So if you click the video, you will see that the same type of discovery pathways work for the electron microscopy. So UT is now the only place, at least in academia in US, where we build the fully cloudified microscope. We can send data to the cloud resource. We can analyze it using the standard SEM or customized workflows. And we basically can tell the microscope to explore the structure property relationship one particle at a time. So if you go to the next and the last slide, where does it bring us? So the next challenge for us is to get past the sample preparation bottleneck. So we need to somehow learn how to take tens and hundreds of samples and compress them within a single electron microscopy sample. And the important message is that we can do that, and I'm happy to stop here.
Thank you, Sergey. So the sixth article that we had in the issue is titled "Frontiers in Polymer Materials Sustainability and AI ML-based Self-Driving Laboratories." And the author is Rigberto Advincula, Governor's Chair of Advanced and Nanostructured Materials and Group Leader at Oak Ridge National Laboratory and the University of Tennessee at Knoxville. So for this and the next article, I'm going to request the authors if they can take 10 minutes so we can have some time for the panel discussion. So, Gobet, please go ahead.
Yes, please, Amit. Sure, try to get this on schedule. And I'm a polymer chemist. I like to synthesize things. I like to design on the molecular, macromolecular level. This collage simply says that when we talk about large molecules, we call them polymers, macromolecules, or sometimes plastics. The origin really is as basic as the bond-to-bond connectivity, carbon-carbon, all the way to self-assembly, directed assembly, and different types of microstructure branching. In fact, enzymes to a certain degree is the most complex of what we can associate with the macromolecule. I really appreciate the convergence with the other authors and speakers today. The big picture really is AI, self-driving labs, data is converging on a class of materials. And very specifically this talk, I focus on macromolecules or polymers or plastics. Next, please. So when we talk about polymers, not only the microstructure, the assembly, but we are talking about sequence. Sequence reaction, since you build this up from molecule to molecule or monomer to monomer, defines eventually the property and what we call structure, composition, even processing property relationships can be traced to the DNA, quote unquote, of the material. And this is the essence of the Material Genome Initiative. How can we bring molecular to mesoscopic to macroscopic in the real world, in a commercial space that we all appreciate and even, as mentioned earlier, be for the competitiveness of the United States. Next, please. So you can see here, plastics is all over. Uh, Plastics, whether we call uh, plastic bottles or for compounding or additive manufacturing, is really just a subset of the class of materials called polymers, which includes rubber, thermosets, coatings, packagings, composites, you name it. Next. So at Oak Ridge, I just want to emphasize that this is one of the biggest communities within the national labs, from simulation, deuteration, characterization, additive manufacturing, and now self-driving labs. We would like to make a difference, not only in terms of basic science, but conversion or translation towards industry. Next. This slide probably did not translate well during the conversion to PDF. Um, this is really the space I've been working on in the area of additive manufacturing. So as a chemist, we've done a lot of polymers in the past, but the last 10 years, we focus a lot on additive manufacturing. You might say this is the digitalization or the use of tools based on CNC movement towards democratizing new materials and innovation towards new functionality and applications. And we've been at it for the last 10 years. Next. Now, I'd like to specifically talk about flow synthesis. I know a lot of things that have been shown by Benji and Bilad looks at high throughput synthesis and even characterization from Sergey. I like to bring this point that what is missed between translating from bench scale or even atomic scale science, catalysis, all the way to a chemical plant is that we are not able to rapidly optimize. We are not able to study parameters for reaction engineering. We are not able to scale up enough samples to do further investigations. In fact, there's another industry that has done this very well. It's called the drug industry, the pharmaceutical industry. The pharmaceutical industry uses a lot of flow chemistry synthesis to make their APIs, chemical intermediates, explore different ways to do asymmetric synthesis. And we can learn something from the drug industry on how high throughput instrumentation, synthesis, and AI is being applied. In fact, if you go to literature, AI and the use of machine learning, whether it's modeling or looking at multi-step synthesis, is very much a part of the organic chemistry slash medicinal chemistry regime. And that's where you find a lot of things we can borrow from, whether it's an API drug or the synthesis of new enzymes. So we have been working on this area of flow chemistry synthesis, and this is really the background of how I'll describe to you the self-driving lab that can make a difference or meet the mid-scale, if not the bench scale gap between what we do in the lab and what is really needed by industry. So AI really impacts a lot of these industries from banking to manufacturing. But an urgent mission, the Genesis mission, actually, as pointed out, one of the biggest bottlenecks will be high throughput experimentation. How do you translate the findings, the simulations, the calculations into things that can be further optimized or even produce a lot of data, real data or standardized data, instead of relying on large language models from past literature? Next. And so, as you can see in this diagram, the devil is in the details, or even a famous scientist like Max Planck said, simulation and poetry is the same. It's called imagination, whereas the real thing is the experiment. So unless you're able to iterate experiments, perfect it, if you may, train data or match it with the algorithm that you develop all the way from statistics to more complex neural networks, you will not find out what the real thing in ways that a closed loop system, a self-driving lab allows you to do this iteration faster and faster with all the tools we have in mechatronics, robotics, and of course, edge computing. Next. So about 3 years ago at Oak Ridge, we tried to answer the question, how would a laboratory look like if there's no person in the room? Literally, the experiment is done by itself, and the self-driving lab is able to operate with minimum human intervention. And I can tell you, as most of you have already made the conclusion, the human in the loop is not going to go away. The expert in the loop will be needed for a long, long time. If there are gaps and pieces that are being filled today that here, all this AI tool converges towards getting and building up more data that we can use to improve the experiment, to improve the models, and so on. So as you can see here,
We lost you there.
okay.
You're coming in and out from the volume.
We the shoulder here.
Well, we're hearing very breaking sort of sound every now and then. Jesse, is it just me hearing that?
No, I think there's a problem.
Yeah, it's
Yeah.
breaking up.
The
Okay.
internet's breaking up.
Rigoberto, your sound is bad. I don't know if it's your connection.
So, Gilbert, we can't hear you, and your screen is frozen. So we can't, your image is frozen. We can't hear you
You just
also.
moved. Maybe you want to turn your video off.
Yeah, something here.
Yeah, try that.
Is audio better?
Yeah, this is good. Please go ahead.
Okay, so the self-driving lab here is a bench scale system. Many things in parallel to microfluidics is actually done these days on a continuous flow chemistry setup. And very interestingly, the drug industry is turning into this as a way to, of course, synthesize and scale up chemical intermediates and APIs. Next. So as you can see in this diagram, the ability to control the reaction and monitor the reaction at the same time is quite powerful, especially when you have a high performance computing platform and an edge computer that is able to do both. And therefore you have a virtuous circle or cycle that accelerates the feedback loop mechanism. And if you tie it with an exascale computing and the cloud, you're able to massively gather and store data. At the same time, calculate, simulate all the way to the quantum mechanical level. Such can be done with an exascale computing. This facility exists at Oak Ridge National Lab. So just to demonstrate one example that among the many experiments we've tried to make a contact lens by controlling the copolymer ratio and monitoring the reaction by NMR, IR, and Raman. And the result was we obtained a contact lens that still needs to be perfected. So what I'm describing here is really a ecosystem by which laboratories of the future will be done, where a lot of the AI and machine learning simulation and modeling can be done in a high throughput manner with its own operating system, access to powerful computing, sensors, mechatronics, and in the future, I predict a lot of democratization will take place, meaning many laboratories can have it at a lower cost. Even 3D printing can be a way of an open source manufacturing and so on. Next. So we've been busy as well as I can see many laboratories turning to AI and machine learning for materials sciences on the basic level all the way to process optimization in engineering. So with that, I'd like to thank you and I hope we get back on track with time.
Thank you so much. So we can go to one more slide. All right. So the last article we had in this issue was titled Accelerated Materials Discovery Through the Power of Artificial Intelligence for Energy Storage. And the authors were Arumugam Mantiram, the George T. and Gladys H. Abel Endowed Chair of Engineering at the University of Texas at Austin, and Tian Singlai, who works with Mantiram in his lab. So, Ram?
Next slide, please. So first, to give a warm-up, in a battery, we will have a negative electrode anode and a positive electrode cathode and an electrolyte in between them. During charge discharge, the lithium ions will be flowing back and forth between the two electrodes. The electrons will be flowing through the external circuit. So we are worried about energy density or user time. That's a product of cell voltage and amount of charge stored. In this case, the amount of lithium ion stored per unit volume or per unit weight in these materials. Cell voltage is the difference in energy or related to the difference in energy between the cathode and anode, which you see on the right side. Can you advance one more time? So during charge discharge, the redox energies will be changing. That's why you have sloping in the voltage profile. But there is a constraint. The energy levels of the cathode and anode have to be within the band gap or between the HOMO and LUMO of the electrolyte. So if you take other conventional batteries, lead acid or nickel cadmium or others, we use water-based electrolytes in which that electrolyte stability window is small, so we can't get more than 2 volt. In contrast, in lithium-ion batteries, we use water-free, non-aqueous electrolytes. Therefore, that electrolyte stability window is wider, so we are able to get 4 volt. Next slide. So, considering the battery performance metrics, we have to at least look at 6 parameters. They are listed here. And among them, cost and supply chain challenges is the most dominant issue as we move forward, as the industry is expanding exponentially while having adequate safety. And it is hard to control or have all these parameters together in a material system or in a battery chemistry system. That's where the challenge is, and that's where the AI can really help as we move forward. Next slide. So in a battery, for example, in a lithium-ion battery, about 75% of the cost is coming from materials. In that 75%, 50% is coming from the positive electrode cathode. So that means cathode is the most expensive because it involves a lot of expensive or less abundant metal ions. We started the technology in 1991 with lithium cobalt oxide. The trend during the past 35 years has been to slowly replace the cobalt with nickel and manganese because they are a little bit more abundant and less expensive. That is with the NMC cathode chemistry. The other material is lithium iron phosphate, for example. That's a polyanion cathode that uses iron. That is the cheapest element. Next slide. So, as I pointed out earlier, on the left side, you see it started with lithium cobalt dioxide. Trend is to replace cobalt slowly with nickel and manganese or nickel and cobalt. Those are all called the NMC or NCA cathodes. They belong to the same structure. The other category is polyanion oxide cathode. That is the LFP. That is exclusively with iron right now. With anode started with coke and then graphite, and then now we are with silicon and graphite composite. The right side you see the emerging next generation technologies where the interest is to replace all these expensive metals with, for example, sulfur or air to give us lithium sulfur batteries or metal air batteries, or even replace sodium. Then we can have sodium ion batteries with 3 possible cathode chemistries, or eliminate any mined metal, any of these transition metals, and you replace lithium also, then one can have sodium sulfur battery. I call it as mined metal free battery because sulfur is abundant in the petrochemical industry as a waste, and sodium is abundant in the ocean. So we won't have any supply chain issues. Now all the ones on the top are currently with liquid electrolytes. They are flammable, so they can lead to safety issues. So the other trend is to replace liquid electrolyte with solid electrolyte with most of these chemistries. So that is all solid state batteries. They will have better safety because the flammable liquid is eliminated. They can also give higher energy density. In addition to this, in all the technologies listed above, the electrodes are solids, the electrolyte is liquid. The other option is to use solution or liquid electrodes. So that is called redox flow batteries. The energy density will be low, but that is particularly attractive for grid storage. Next slide. This is where you can feel the challenge. All the practical cathode is the most expensive. All the practical cathodes we use, they were all concepts developed in 1980s. With one group, that is John B. Goodenough's group, he got the Nobel Prize in 2019, both at the University of Oxford and at the University of Texas at Austin, involving 3 visiting scientists, not students, from 3 different parts of the world. Mishishima from Tokyo University came, worked at Oxford with lithium cobalt dioxide, left. Michael Thackeray came from CSIR lab, South Africa, did spinel, left. I came from India, from a university, worked with iron-based cathodes, polyanion cathodes. Then I end up coming from Oxford to here, and I stayed here for the past 39 years. Now, when you go from left to right, the cost is reduced and also the safety is enhanced because the polyanion, sulfate, phosphate, all those hold the oxygen very tightly, so they don't release oxygen, so safety is better. More importantly, iron is the cheapest metal you can think of, the 4th most abundant element on the Earth's crust, and there is no supply chain issue. And 93% of mining in the whole world, 93% of mining in the whole world is iron. So we can't get anything better than iron to use in the battery. Next slide. So this is more or less same. The business is cost is the most important. Cost and supply chain issue is the most important aspect. So you're slowly eliminating cobalt, going to polyanion LFP, for example, and then eliminating lithium, that is sodium ion batteries with less expensive metals, no transition metal, that is lithium sulfur, or eliminating all of these weird expensive metals, that is no mined metal, so sodium sulfur or sodium organic. These can be used with liquid alkali or all solid state or even redox flow cells. Next slide, please. So now, right now we are at silicon graphite. There is a lot of interest to use lithium metal itself. That will have a lot of safety problem, but it can give higher energy density. We use liquid alkali. There are safety issues associated. So if you replace liquid with solid, you will have better safety and better energy density. The right side I have already shown. You can see the figure on the right side. That is the redox flow battery. You see a tank of, for the anode, it's called anolyte, and a tank of solution for the cathode, that is called catholyte. So you can store a lot of liquid chemical. So that means the energy density. You can store a lot of material and pump it, use it, so that will give higher energy density. That's why it is good for stationary storage. Next slide. So now, as I pointed out earlier, there are several parameters we have to satisfy or get everything. That's very hard. And largely, as I mentioned earlier, the chemistry, cathode chemistry we use is what developed 40 years back, the 1980s, 45 years or close to 50 years back. And that's what we use. What has happened during this period, 4 or 5 decades, is enhancing or improving the engineering associated with these materials. That's all what has happened. So how do we develop new chemistries, new materials, new battery chemistries? That's where the AI can be very helpful. There is a lot of data in the literature. So one can use literature mining, data mining, that can be used to train models, and that can help to generate next generation battery materials and battery chemistries, and then predict properties, and they can also be used to validate. And so it is kind of an active learning and closed loop optimization. Next slide. In a little bit more detail, as I mentioned earlier, literature mining, machine learning based computational models, and high throughput experimental methods involving robotic systems, active learning loops, and self-driving labs. On the prediction and optimizing battery material side with the electrode materials, AI can be helpful to predict crystal structure, density, conductivity, capacity, cycle life, redox energy, thermal stability, safety, and rate capability. On the electrolyte side, liquid electrolytes, again, conductivity, solvation structure, intermolecular interactions. Solid electrolyte side, ionic conductivity, structural stability, and electrochemical compatibility. So a lot of things involved, very hard. By lot of things are happening trial and error basis, so the AI can be very helpful. Next.
Ram, could we summarize soon?
Yeah, I'm almost done. So this is again the same thing I talked about. It can help to develop new cathode, anode, and electrolyte materials. Next slide. Two examples of labs: closed loop autonomous lab for AI assisted new inorganic electrode material development at Berkeley, particularly with Professor Gerd Ceder's lab. There they are doing autonomously selecting candidate materials, synthesizing and characterizing them, and using ML to analyze the resulting data and propose the next set of experiments. Next slide. This is another lab, particularly to develop electrolyte at Carnegie Mellon University. Again, combines active learning with high throughput experimentation. Develop formulations that improve ionic conductivity and electrochemical performance. Next slide. Anyway, overall future experimental infrastructure must expand, data quality and accessibility must be improved, and then tailored and more accessible AI tools and platforms for battery research need to be developed. More importantly, intimate collaboration and communication between experienced experimentalists and computational experts will be necessary. Next slide. I'm thankful to all the people who have worked with me. This is my current group as well as the funding agencies. Thank you very much.
Thank you, Ram. Can we go to the next slide, please? And I think this is also the time to go for the panel discussion. So, I mean, originally we have enough interesting questions to discuss, points to discuss. We could have a panel discussion for a lot longer than we have time left. So we will have a selective set of questions that we will pose to our distinguished panelists. So, Chessie, I believe.
How about you frozen?
He was just being moved over to the other format.
Okay.
And then here.
Ah, yes.
All right.
If you lean forward, you're much bigger than
So if you have questions to the audience, if you have questions, please put them in the Q&A on in the Zoom, and I'm going to request our panelists to go ahead and answer them on, if they can, while the panel discussion is going on. We have 15 minutes, so we will try to take a few questions and get some feedback from the panel. So let me start with one of the important questions, and it always has to do with dollars and funding, right? So what is the current funding for MGI in the US? Has a case for economic and national security been adequately made by both scientists and federal agency managers to increase US investment? There is a lot of private investment in this space also. So what is the role of federal investment? What pre-competitive areas need development that federal funding is ideally suited for? And perhaps you all can take and focus on the functional area that you're most connected with. So anybody who wants to go first can just go ahead and start.
I can jump in for a sec, but I'm sure my peers here have lots to say. I mean, so there was a lot in that question. First of all, the thing that I gravitated towards was the role of government versus private industry. There is now a small number of fairly well-funded startups in the autonomous lab space. Some big announcements in the last few years, a few $1 billion. There's a lot still that needs to be done, as was said. This is, in my opinion, the future of R&D writ large. So while materials is a very large example, obviously there's the whole biospace, and it's really a continuum, right? So there's obviously a huge role for the government in making all of this much more accessible, and of course training the next generation of people who are going to do this. Over.
Anyone else who wants to jump in? And you can always also just raise your hand and I can see you as a virtual panel here. Any other comments?
I think I agree with that. More needs to be done in the infrastructure development. It's the beginning, very, very beginning. So I think we need to put more resources for the infrastructure development.
Benji?
Yeah, I would just point out that the research is what gets all the attention, the results, the better quantum devices or molecules. What costs a lot of money is the infrastructure. So that's things like better automated analytical systems, spectrometers that play well with robots or easily automated. And so that's very expensive and it's harder to fund. And it's really, frankly, a good pre-competitive area of investment that, for example, academia can't fund well and industry might not want to pay for. So I think it's a good area for the government to invest.
Okay. Well, let me take on a different question now, and so perhaps just to get people excited as well as the funding agencies. So this question relates to that. What is the most compelling example where investment in a self-driving laboratory resulted in a transformative finding that made a radical difference to performance and subsequent commercialization? Anyone? Please go ahead. Go back.
Yeah, Amit, I appreciate, and that question really can be answered by several of us. And I would say look at the drug industry and in the near term, because of their convergence and partnership with NVIDIA, with Thermo Fisher, a lot of these automated tasks and self-driving labs will translate to chemical intermediates and APIs that can be very profitable. The answer towards democratization of self-driving labs may lie in how universities will train the future students in chemical engineering, material science engineering to do Python scripting, robotics, mechatronics, or even 3D printing and bring it to chemistry. That's one example. And then a very short comment on the funding. I would say PPPs, public-private partnerships, is the way to go because of the infrastructure that is necessary at the beginning. But I can see a lot of startup companies coming to this fold because they can see the bottleneck of high throughput synthesis, testing, characterization really is the way to translate scientific findings at a much faster rate.
Jim?
Sure. So just quickly, I would reiterate what Rigoberto just said. I think you may have seen in the last couple of days that Lilly and NVIDIA just announced a $1 billion partnership for autonomous labs for drugs. So, I mean, the money is starting to flow. And if you want to see where the money is going to go in materials, it's often a very good idea to watch pharma, right? It's very well capitalized. And often is sort of the leading edge for what will happen there. So I'll turn it over to Milad now.
Milad?
So in terms of the impact of self-driving labs, I think in any high-dimensional material synthesis problem, doesn't matter what kind of material, as long as the parameter space is known, I think STLs have made significant advancements. If you look at the solution processable materials, for example, the materials identified by autonomous experimentation have outperformed any benchmarks. So it's all about how do we know? Do we know the parameter space? Is the high dimensional problem? If yes, do we have high throughput experimentation method with the right characterization? Then yes, STLs can find a solution within that known parameter space much, much faster than the current gold standards in industry or academia. Now, going beyond the problems that we don't know the parameter space, I think they're going to have self-driving labs are also going to have a huge impact. But then we need to develop the engineering infrastructure that can allow you to find the failures of the platform because you're entering unknown territories that you don't know if your hardware is going to fail or not. That's an engineering challenge. Are they going to have an impact? Absolutely, yes. And they've already had significant impact in reducing the time to solution for catalysis, for example. They can right now do very fast process optimization using their self-driving labs within days instead of years. And right now it's a standard process. So that's one part of your question. In terms of pharma has been very, very advanced in terms of investments in high throughput experimentation. They were probably in the frontier of high throughput experimentation about 30, 40 years ago. And right now, material synthesis and material science is trying to catch up. And as Jim said, the recent announcements in investments of pharma industry in AI is a good indication of pharma has already seen that potential. And we're all hoping that material science companies are going to follow next.
Okay, well, thank you. So let me ask you one last question. That's all we have the time for. And it's going to be for education and training of next generation scientists. Are we doing a good job? Should the emphasis be more on transdisciplinary positioning for training people to work in MGI? Or do you feel scientists need to be well versed on all the key components of MGI? If so, what depths should they be trained in? Very short answers, please. Go ahead, Sergey.
So I think that we absolutely are doing very poor job on training people for that. And in fact, we are almost in the position of the perfect storm, where the classical CS workforce have been developing for the 30 years. So the advent of the co-pilots and coding assistants basically erased 80% of these jobs and very much narrowed the space. If we want to use machine learning in the domain sciences, primarily we need a domain science skill. So I think that a big part of the training would be the hands-on practice, all the way from Raspberry Pis and Arduinos to building things upon the lab robotics and so on. But activation energy to do machine learning now is exceptionally low. The lab skills and capability of build a bridge between the ML world and the real world is something that is really needed.
Benji?
Yeah, I agree. I would say we do need to do a lot more in being able to synthesize our research workflows with decision processes brought in by AI and autonomy. And a key factor to that is making sure that our students have access to those hands-on activities, whether it's Raspberry Pi or open source software, very accessible hardware. If you don't get to do that until you're late undergraduate or graduate school, it's really too late. So you really need to drive that down to the grade school level. Over.
And Ram?
So improvement is needed. So work or research happens in a compartmentalized fashion. Experimental people just do experiment, computational people do just computation. The students then are trained just experimentation or computation. The dialogue doesn't happen. So we need to have a better integration, better communication between the computational people, modeling people, simulation people, and the experimentalists, involving human intervention so that we can do a better job of what we can do.
Rich, a short comment?
I just wanted to emphasize Benji's comment and add, I think entering into undergrad education now, just like we expect people to be versed in word processing and Excel, et cetera, they're going to be expected to be versed in all tools of machine learning, large language models, and Arduino interfaces a digital world with the real world. I think that's a given. But from an undergrad point of view, a lot of the things we're talking about is tools of operation research and systems of systems analysis. And so having a workforce that better understands and thinks at a system level as well as an operations research level, so it can understand workflows, is a important skill to be able to truly optimize and utilize a lot of these techniques we're talking about.
So, I could engage you all for a lot longer in this nice panel discussion, but we've only got a few minutes left, and so I think it's time to wrap up. I want to thank all the panelists for their remarks. I would like to thank our NAE, the 4 NAE staff in particular who made this webinar possible. David Butler, he is the J. Herbert Holloman Scholar and also editor of The Bridge. Chessie Briggs, who is the program coordinator. Amechi Okpabi, the audio-visual coordinator, and Kristen Kohler, director of NAE Outreach and Communications. And most importantly, I'd like to thank all the people in the audience for attending. A recording of this webinar will be posted on the NAE Bridge page for those who could not attend. And thank you all. And I know that Ron has some comments.
Before you sign off, Amit, if I can just have a moment.
Please.
Number one, I want to thank you for assembling a wonderful issue of The Bridge, but even more for putting together this fantastic webinar. I think as an inaugural, it's just showing the way that this can be done into the future for The Bridge, and I'm very, very pleased with it. Secondly, Jim began by talking about the impact that MGI has had on Tesla and SpaceX. But if you think about fusion energy and quantum computers and solid-state batteries and a whole host of new technologies that are just developing, new materials and computational material science and engineering as manifest in MGI are going to be front and center. So I think this has been an enormous accomplishment today. And as editor-in-chief of The Bridge, I can't tell you how pleased I am. So I thank you all, and I wish you a good day. Thanks very much.